In this video I will compare receivers on 7.2 MHz with signal generators as well as with real antenna signals. And here is the setup, starting with a low-pass filter at the antenna to prevent the FM stations from saturating these wideband amplifiers that give a lot of gain. After these two first amplifiers, I have an attenuator and then a hybrid where I can add signals from 3 signal generators that are combined with a proper power combiner from mini circuits that isolates them from each other. And they have a stepped attenuator. The output from this hybrid is amplified by 13 dB. Inside there is an MGA 3689. And then there is 6 dB more gain from a more powerful device, BUK 75150. And then a stepped attenuator. And again a 6 dB gain with BUK 75150. After that there is a 3 dB attenuator in order to present 50 ohms approximately at the notch frequency. So this amplifier will not look into a short circuit. Then the notch filter, followed by a 6 dB attenuator and a 9 dB coupler where I connect a spectrum analyzer to look at the signal that passes through here, and then a minus 20 dB coupler where I can inject a signal from another generator at the center of the notch. And then comes a 6-port Wilkinson splitter. And this thing needs to see 50 ohms in order to provide isolation between the outputs. And that's why I have this 6 dB attenuator here, to have isolation also on the notch frequency. And the outputs all have 6 dB attenuators, and the connected receivers are the Perseus, the Airspy with the Spyverter, and the Airspy HF Plus, and the Airspy HF Plus Discovery, and the SDRPlay RSP1, and the Afedri, the NET Afedri. To show what this total system is, I connect the network analyzer from the antenna here to this point here at the output of the notch filter after the 6 dB attenuator, and look at the screen of the network analyzer. The frequency response is fairly flat from 300 kHz to what might it be? 12 MHz, 12.5, and 300 kHz. It drops by 10 dB at about 180 kHz due to the BUK amplifiers. And the steep fall off here is because of the notch filter. And here is the notch, which we don't see well on this network analyzer. I have to zoom in to see that. But the gain 22 dB that we see here is actually 50 dB, because I have here the stepped attenuator set to 30 decibels. And I can reduce that 10, and I'm not quite saturated, but there was some change. So I can reduce the power of this network analyzer, minus 60. And then we have the correct pattern back, but there are some problems at very low frequencies, noise problems. Anyway, the spectrum, the response from the antenna to the radios is fairly flat, from say 200 kilohertz to 12 megahertz. So all interference in that range will affect the radios in this testing I'm doing today. Here is the antenna input amplifiers, hybrids, more amplifiers, and that very first attenuator. And this is the three-way power combiner, and two more attenuators. And then the signals goes to another place. This is where I had the interferometer before. All cables are well grounded here, and the signal goes into the notch filter. DC to 13 megahertz is marked. And then the couplers and the Wilkinson splitter and the attenuators. One of them is this one, set to 6 dB, and this one also. And then the signals go out into the various receivers. SDRPlay Airspy and Spyverter, HF+, HF+ Discovery, no, another HF+. This was the HF+ Discovery, and this was the ordinary HF+. And then the Perseus is inside the aluminium foil because I needed it more quiet when doing other experiments. And then the Afedri, the network Afedri. The time is 2:30 in the afternoon. There is not much in the medium wave range, but we can see occasional big pulses. And here is some very low frequency. I can click on max hold here, and it will remember things. These pulses that come occasionally. And general noise pulses. Here is the time domain. You can see these big pulses coming occasionally. An amplitude in the order of half a volt peak to peak. So very big. If I increase sensitivity of the oscilloscope, you can see the normal radio. We have a strong signal at about 350 kilohertz, and then all the HF 8 megahertz or something. And the level here is, the HF spectrum is something like 25 millivolts. So those pulses are really strong, but not very frequent. This is the Airspy HF Plus with the signals that you just saw on the spectrum analyzer and the oscilloscope. The yellow track here is the signal to noise ratio. It's computed by Linrad by taking the signal here through a very narrow filter and compare it to the total noise that is this spectrum. And if I remove that antenna signal, you can can see there is some time delay, but here is the signal to noise ratio when the unit is not affected by the strong signals. But here I'm back. And I switch off that and switch on here. This is the HF Plus Discovery. And again, I switch off the antenna signal. And I'm a little bit surprised to find that the signal to noise ratio is not quite as good. But the influence of the interference is a little bit smaller. Here is the Airspy+Spyverter. I have set the gain for optimum performance at about 18. Then the noise figure is about 68 to 48, that's 20 decibels worse. But the interference is not so horrible from the pulses and all the stations. If I turn up sensitivity here, see there is interference. I remove the antenna signal. And it doesn't make much difference. This is the SDRPlay RSP1, and it's affected by the antenna signal. I remove the antenna signal. Put it back. This is the Afedri, and you can see the pulses. Now this is Linrad, so the AGC is more favorable. It has a very short release time. You can make the release time long, let's say 6, and the attack time short. And then it doesn't sound so well anymore. So attack 5 and release 0. Finally, the Perseus. So here is the Perseus, and there is no sign of any problem. So I turn up the level by 10 decibels. Ten more decibels. And 4 more. And that's all I have. And now we can hear something. But not much. Now the noise figure of the Perseus is not comparable with the noise figure of the HF+. So to be a little bit more honest to the radios, note I'm running them without making the noise figure equal to start with. I have calibrated this signal to noise measuring on the loudspeaker output from the Perseus to show 0 for the Perseus. Means a noise figure in the order of 22 decibels. That's with these attenuators set to 0 and 10 decibels on this one. So it is within the range where the Perseus has no interference that can be visible in the current circumstances of the signals from the antenna. Here is the Afedri. The signal to noise ratio is worse by 2 decibels. I can try to improve that by changing the gain and go from 23 to 26. And we get much more interference, but this is clearly better. But we have intermodulation. I remove the antenna signal. And now the noise figure is 2 decibels better than for the Perseus. Well, that's the Afedri. This is the RSP1, and the signal to noise ratio varies quite a bit, but on the average it's not very different from the Perseus. I can try to change the gain reduction. It's now 34. Now it's 28, and I start to hear intermodulation things, like here. So this is not good. And this is maybe a little better, but not much. So I reduced the antenna signal by 10 decibels. There are still these pulses coming through. "20 decibels, then I don't hear them anymore. So I need to set 18 decibels here. attenuation on the antenna signals, plus the 10 I have had here all the time, to not have this interference. And then I can look for the optimum setting of this. Seems to be 37, maybe even 32, yes. And away with the antenna signal. And that makes a small improvement. Again, the Afedri. This was the SDRPlay. Here is the Afedri. And I need to set 16 decibels of attenuation to not hear those pulses. This is the HF Plus Discovery. And here are the settings I'm using now. And you can see the pulses, but the signal to noise ratio is 14 decibels better than with the Perseus. And these pulses are not terribly annoying. But if I want to have them disappear, I have to insert more attenuation. Well, so 19 decibels is what I have to set. Well, even 20. To get a 14 dB better signal to noise ratio. Then I turn on much more antenna signal. And here we can see the noise figure gets lower. The noise floor goes up. And that's because the AGC starts to do something. Now I have to turn up on this knob to get more signal. And we can hear the signal, and the signal to noise ratio is not so good, so I have to go maybe here. Similar to the Perseus. That's 9 dB, but I have increased the signal by 10 dB here. So it's roughly 0 and 0 to have a performance similar to the Perseus. This is the Airspy+Spyverter, and I have adjusted this gain control for best performance with this attenuator on 0 and this one on 10. And the noise figure is not good enough, so I attenuate by 10 dB. And this is clearly better, and I can optimize this gain control, maybe. Doesn't make much difference. So the noise figure is not so good here. 6 dB higher as compared to the Perseus. I have replaced the Spyverter by another one, and that makes the noise figure about 2 dB better. It's now, well, I don't remember, but it's a little bit better. Now it's 4 dB below what I had on the Perseus, and that is with maximum gain. Now I turn on the antenna signal and set the gain control for optimum. That's 17. I lose too much noise figure. This seems optimum. And then I look for how much attenuation is needed to not hear these pulses. To not hear the pulses anymore, as you can see here, I need to set 11 dB, and then signal to noise is 4 dB worse as compared to the Perseus. Here is the HF+, the original one with 2 antenna connectors. I have these pulses strong, but signal to noise ratio is very good. To not hear these pulses, I have to set some attenuation, like before. So, I have to set 34 decibels. With HF AGC off and 18 dB of attenuation, the noise figure is similar to what I see on the Perseus, and that is with an attenuator setting of 17 decibels. This is the HF Plus with a modest antenna signal. It looks like this, and I'm adding a signal on 1.5 megahertz now. Here. The level is minus 15 dBm. That causes the signal to noise ratio to drop by, well, from here to here, 4 dB. So I increase the level of that signal. Oops. Well, here the AGC turns down the sensitivity, and now the sensitivity is equal to what I have with the Perseus, and that is at minus 7.5 dBm at 1.5 megahertz. So that was the Airspy original, the Airspy HF Plus, the one with 2 antenna connectors. And here is the HF Plus Discovery with the same signal that made the noise figure not so good anymore for the HF Plus. You can see here, and I increased the level of this 1.5 megahertz signal by 10 dB. Well, here there is a problem. Here sensitivity is the same as for the Perseus with the HF Plus discovery. But you can see something is non-linear here. Probably an amplifier saturated. Or maybe the spectrum analyzer. Well, so the level is marker plus 12 dBm for medium wave stations. That causes a problem. Just checking non-linearity problems. Here is the Airspy plus the Spyverter at 18 in the gain control. And I increase the level of the medium wave signal. That was only 2 decibels. And I switch it off. So at this point there is about 2 decibels loss of signal to noise ratio. That's probably too much. Here. Because that is probably gain compression, so it's associated with a lot of distortion. Now I have only 1 signal on the medium wave, so I don't see the distortion, I just see the compression of everything. But this is roughly the strongest medium wave this can take, and that's minus 12 dBm. Here is the Afedri, and I turn up the medium wave signal in steps of 1 dB. And here is a threshold of some kind, so I go back. Well, like this. And the level is minus 11 dBm at 1.5 megahertz. And here is the RSP1. At gain reduction 32, and this is the signal to noise ratio, and I increase the medium wave in 1 dB steps, and I can hear there is a degradation here. So this is the point where degradation starts, roughly. Like that. And this is minus 27 dBm. So this one is rather sensitive to medium wave, causing interference on HF bands. And now the Perseus. And of course it shows 0 as I calibrated it some time ago. The signal to noise ratio, and I turn up the medium wave signal. This is the most signal I can generate with this setup, and the marker shows plus 13.5 dBm, and you can see there is some compression, but well, there are good filters in the front end of this radio, so it is fairly immune. Now I have two signals of equal amplitude, one at 1.5 megahertz, the other at 8.6975. That means that the difference frequency is very close to the signal, to the frequency of the desired signal. And I changed the levels of these two together and look at what point they have the same level in the different receivers. So right now I am using the RSP1, and you can see here I need a little bit more. At this point they have the same level, and I have removed the antenna signal, so it's only these two. And the level is minus 40. And here is the Airspy+Spyverter, and I didn't change the levels. It's still minus 40 dBm. This is the Afedri, and the levels are still the same, and I didn't change anything. So the Afedri is also minus 40. Here is the HF Plus, and I have to reduce the two signals a bit to make the difference signal equal to the desired one. It's about here, at the level of minus 46. And this is the HF Plus Discovery. And I have to turn on more signal here. Well, like this, and that's minus 22 dBm. And finally the Perseus. Well, hard to see, there's too much light in the room, but anyway, the Perseus is running here, and I don't see the difference frequency, so I need more. Here it comes. Oh, it's at the other side. Here, now they are equal in level. And this is at minus 14 dBm. So here is the level I have observed for these radios producing a difference frequency from 1.5 and 8.7 megahertz. And that is with the same level into all of them. So the noise figure is different from these radios. This is not a fair comparison really, but it's something that people might do. Just run the radio on your antenna. And then these are the results one gets. Now I'm injecting a signal 30 kilohertz below the desired frequency, and I'm listening to the Perseus. And you can see here this loss of signal to noise ratio is very small, and I add 1 more dB and I lose a lot, but the Perseus is saturated. The red indicator is on now, ABC clear. The level for this is plus 2.5 dBm. This is when it is not saturating. Here is the Airspy with the Spyverter, and the noise figure is a bit lower as compared to the Perseus. This is the first unit which has a slightly higher noise figure. It's the R2, so it is better from some other points of view that I don't quite remember. So I turn on the signal, and I have lost 2 dB. This is much more than that. So a 3 dB signal to noise ratio degradation is obtained at minus 36 dBm. And here is the RSP1. And I turn on signal until I see a degradation. Well, it's about here. Maybe a little more. And that is minus 54 dBm. And here is the Afedri. And I turn on signal. Here I lost 3 dB approximately. And that is at minus 10 dBm. And here is the HF+, and it has a much better noise figure, but it degrades fairly early because of the AGC. So here is a 3 dB loss at minus 33 dBm. And finally, the HF+ discovery. And here I lost 3 decibels, roughly. And that's at minus 39 dBm. The level I'm reading here is not the same as the level into the receivers, because this is from the minus 9 dB coupler in front of the 6-way splitter. So I now disconnect something and connect the spectrum analyzer to one of the receiver input connectors at the 6 dB attenuator at the output of the Wilkinson splitter. So now I have 39.3, and here's the signal going into one of the radios. It's minus 44.5. So I have to correct by 5 dB. So these are the actual levels into the radios in the first test, this IM2 thing, and the 30 kilohertz offset is like this, and here are the radios with the corresponding numbers, and here is for the second order intermodulation, 1.5 plus 8.7 megahertz. Now this video is not as much to get absolute numbers. I have shown. So this video gives an idea about how these radios behave when you connect them directly to an antenna. So it's not a comparison of dynamic range. To do that properly, I would add attenuators to make all the receivers get the same noise figure. And then things will look a little bit differently, and that will be another video.